Hello, ladies and gentlemen. So we have a couple different things to talk about in this lesson. We're going to take a break from our series convergence tests. We've done all but the ratio test, which we'll do next time. So this one, we're covering two different things in one lesson. The first thing is called error bound, and that's what this whole front side of the notes is all about. And then the second thing we'll talk about is whether a series converges absolutely or whether a series converges conditionally. We'll talk about that. So first of all, when you're summing all the terms of an alternating series with a finite number of terms. So imagine if you look down here to make this make a little more sense. If I have an alternating series, and let's say I actually wanted to calculate the sum of, the first certain number of terms. Well, I can get a value. I can actually figure out what those terms are, add them up, and I get a value. Obviously, that value is not going to be the same as the sum of all of the infinitely many number of terms, meaning the sum of a partial series is going to be different than the sum of the entire series. Okay, so here's what we're going to do today. If we want to calculate the error, basically, if we would sum up, say, the first 7 terms, I'm using this as an example. If we want to calculate how far off is that number from the actual sum, we're able to calculate that. We can't figure out the actual sum. I've talked about that. The only one we can figure out the actual value is the geometric series. But the alternating series gets us pretty close to finding the actual value. So if we want to calculate the error, otherwise known as remainder, and so this is the difference between what the actual sum would be and the partial sum that we found. Well, what we do, this is this notation. And this notation kind of confused me when I first started teaching this class, but what this is, S is the sum of the actual series. Like if you added up all infinitely many, this is the sum. Take away the sum of the first 7 or sum of the first 8 or whatever. So this is the difference between the sum that you found and the actual sum, and that's called error or remainder. It's often difficult or impossible to find the actual sum, but we can put a bound on this error. We can figure out how far off that error is. This bound will be the absolute value of the next term in an alternating series. This is the most important sentence right here. This bound will be the absolute value of the next term of an alternating series. Now, I know this is a lot of words, and I'm saying a lot of things, but once I start to do an example, it starts to make sense intuitively. Hopefully you watched that Khan Academy video first. For example, if we add up the first 10 terms in an alternating series, the error will be less than or equal to the absolute value of the 11th term. Essentially, whatever the next term is, that's how far off your value could possibly be from the actual value. That's the most that your answer could be off from the actual value, whatever that next term is. And that's what this notation is saying right here. So this is standing for the difference between the actual sum and the sum you got. That's also known as the remainder. And that value is less than or equal to the absolute value of the next term. That's what this notation is standing for right here. The remainder or error will always be less than or equal to the first neglected term, the next term. All right, so let's kind of do a few examples to make this make sense. So the first question says, find the sum of the series. And notice it doesn't say infinity, it says 7. It wants us to add up the first 7 terms of this series. Now you can do two things. You can either plug in 1, 2, 3, 4, 5, 6, 7 and get your 7 terms and add them up. Or you can use your summation button in your calculator. That should never be needed on the AP test, but it is an option. And I'm just going to tell you what this value is here. And it wants us to find the error bound for this sum and the sum of the infinite series of the same thing. So the first thing I want to calculate is, what is this value? So if I would list out, plug in 1, 2, 3, 4, 5, 6, 7 and add those numbers up, I'm just going to tell you what that is to kind of save some time because I know you guys are capable of doing that. So if I do 1 to 7, -1 to the n plus 1 times 1 over n squared. If I figure out what that sum is, it's this. It's 0.8312414966. Now, I went out that far because I always like to go as exact as possible. Also, you'll see why here in a second. So this is the sum of the first 7 terms. Well, what we need to figure out is what would the 8th term be, right? We added up the first 7. What would the next term be? Not the sum of the first 8, just the 8th term. So if I would plug 8 in for these n's here, well, this would be negative 1 to the 9th is negative 1 over 64. So the 8th term is negative 1 over 64. So what that means is the error bound is the absolute value of that, is 1 over 64. Or in decimal form, so we're going to be doing some decimals, 0.015625. Now, that's still a lot of numbers that I'm throwing at you, but here's what this means. Here's what all this boils down to, okay? This number right here is obviously not what we would get if we added up infinitely many terms of this series. But what we just found out is if we did add up all infinitely many, the farthest that value could be away from this value is 0.015625. Think about that. The farthest this value of the first 7 terms could be off from the actual value is this. That's the farthest it could be off. That means it could be even within this range. This is the farthest it could be off. And that's just from calculating the first 7 and comparing it to infinitely many terms. That's just crazy to me. So what that means is this. If I would add 0.015625 to this number, and I would subtract this from 0.8312 ... I would actually find a range of what the true sum could be. So the actual sum is between whatever I get when I add and subtract this error. So it's going to be 0.815616 and 0.848665. I just arbitrarily pick numbers. But think about that. Just from adding up the first 7 numbers, we're able to determine what the sum of all infinitely many would be. It's got to be in between these 2 values. And I could pretty easily just add the first 10 up or the first 20 up and shrink this range to get really close to the actual value. Isn't that nuts? We can't figure out what the actual sum is, but we can get closer and closer to what that actual sum is. I think that's pretty cool. So what's important to understand is this only works with alternating series. We can't use this idea of all the series that we've determined for convergence. This is specific to alternating series. The farthest your partial sum could be off is whatever the next term you didn't include is, the absolute value of it. Insane! Insane in the membrane, went insane, got no brain. All right. Approximate the sum of the series by its first 6 terms. So it wants us to calculate the sum of the first 6 terms of the series, figure out what the error bound is, kind of like what we did in the last problem, and get a range of what the actual sum could be. That's what it means to approximate. So if I found the sum of the first 6, that would be 0.631944. Just from adding up the first 6 terms, that's the value that I would get. And then I need to figure out the 7th term. What would the next one be? Well, if I plug 7 in, I would get positive 1, and then 1 over 7 factorial, which is 1 over 5,040, which is 0.000198. This one's even more asinine. I only added up the first 6 numbers, and I know the farthest this number can be off from the actual sum is 0.000198. What? Insane. So using this notation up here, because I want you to actually understand this notation, what this means is if I take the actual sum minus the sum of the first 6, which I found that value, that is less than or equal to this number right here. The difference between the actual sum and the sum of the first 6, the difference between that is less than or equal to that next term. That's what that notation is saying. So if I want to figure out my range, well, I just take this number and add it to this and take this number and subtract it. I'm going to actually solve. This is kind of a blast from the past, and we stopped teaching it in Honors Algebra 2 a few years ago because it's not a standard. They said they do it in Algebra 1. But anytime you're solving an absolute value inequality like this, here's how you actually solve it algebraically. We're going to put this number on the other side, but make it negative. I'll explain this a little better here in a second. So anytime you're solving an absolute value inequality, and the reason I'm doing it this way is because this is something that might show up, I don't know. But you can take whatever this is less than, put that number on the other side of the inequality, and you're basically sandwiching. You can, at this point, undo the absolute value, but you're sandwiching this difference between the positive of this number and the negative of this number. And then the absolute value goes away. And then if I want to solve this, just add 0.631944 to both sides. So I'm going to do that. I'm going to add 0.631944 to the left and to the right. So I get 0.631746 is less than or equal to the actual sum, which is less than or equal to 0.632142. Just from adding up the first 6 terms of this series, I know the sum of all infinitely many is within this range right here. Mind-blowing. All right. The next question they might ask you with this is, because they might say, what's the error bound? And so maybe on an AP test, this is the answer to the question, like this stuff over here. But then I've also seen this question pop up. It says, determine the number of terms required to approximate the sum with an error less than 0.001. So it's saying figure out how many terms you would have to add up to guarantee the error is less than or equal to less than 0.001. What this means is we need the next term to be less than, what says less than? So I should do less than. In my note key, I did less than or equal to. I wonder why. Less than 0.001. We need the next term. When I say the next term, that's like the n plus first term. I want the absolute value to be less than 0.001. Here's how we do the next term. I want to take the absolute value of the next term. So what that means is I take this part right here and replace my n's with n plus 1. That would be the next term. So it would be -1. And if I replace n with n plus 1, I would get n plus 1 plus 1. So n plus 2. And then on bottom, I would replace n with n plus 1, and we get n plus 1 squared. This is important to understand because this comes back up in the ratio test that we're going to learn, being able to do this. And I want this to be less than 0.001. Okay, so a couple of things. This looks kind of messy, but we're basically solving for n at this point to figure out how many we would have to add up to make this happen. Well, the nice thing is when we do the absolute value, the whole -1 to this power goes away. This is the part that's alternating. Well, the absolute value just makes this positive. The bottom is always going to be positive because we're squaring it. So I can actually undo or get rid of the absolute value and make it 1 over n plus 1 squared. I want you to understand what I just did. I'm taking the absolute value of that top part, which this is always going to be -1 or 1 anyway. So when you take the absolute value of it, now we know it's +1. And the bottom's always positive too, so the absolute value is not necessary. And I'm dealing with fractions, so I'm going to write 0.001 as 1,000th. And now I want to solve this. So I'm going to go ahead and, just like I'm solving a proportion, I'm going to cross multiply. So I'm going to have, let's see, 1,000, or I guess I can do, I'm going to do 1,000 is less than n plus 1 squared. Then to solve this, I'm going to square root both sides. So the square root of 1,000 is about 31.6. Take away the 1. Now, n is standing for integer values, right? You can't have a 30.6th term. So n, we would just round this up to be 31. What that means is we would have to add the first 31st terms, the 31 terms, to guarantee that our error is less than 0.001. But understand, less than this stuff, but conceptually, we're setting the next term less than that error, the absolute value of that next term. All right. Next, the difference between absolute convergence and conditional convergence. So when we are dealing with alternating series can converge conditionally or they can converge absolutely. And we'll have to decide if it's converging conditionally or absolutely. So it says a series is absolutely convergent if the series of the absolute value of all those terms converges. You know how when we have alternating series, like the first one's positive, then negative, then positive, then negative, then positive, then negative. Well, if we would take all those negative values and make them positive, if that series still converges, even though now all of the terms are positive, then we say that original series converges absolutely. Like it's going to converge whether those terms are positive or negative. A series is conditionally convergent if this series converges, but if you put the absolute value, like if you make all those terms positive, if that series diverges. And before I do these examples here, I want to show you a pretty neat example of that. So we've talked about the harmonic series. We've talked about the alternating harmonic series, right? So this diverges. I guess I should put numbers on there for good notation. We know this diverges. But we also know now that the alternating harmonic series converges, okay? So I want to use what we know to kind of prove this point and drive this point home. So we know the alternating harmonic series converges, okay? We know that. This converges. But imagine that I take that same series and I put absolute value around it. I take that same exact series that I know converges, and I put absolute value around it. So now it's going to take all those terms and make them all positive. Well, all the absolute value does, it just makes this become +1. The absolute value is so cool with the alternating stuff because it just makes the -1 and the exponent like go away. So this is going to be the same as this. If we take the absolute value, the -1 to the n is always going to be +1, so we're just left with 1 over n. And we know this diverges. So without the absolute value, that series converges. With the absolute value, that same series diverges, which means the alternating harmonic series, I'm going to abbreviate like this, the alternating, that doesn't make sense. That's alternating series test. The alternating harmonic series, I wouldn't abbreviate this like on the AP test, FYI. The alternating harmonic series converges conditionally. Meaning if we take all those terms and make it positive, it no longer would converge. Converges conditionally. All right. So if the series with absolute value converges, then it does it all the time. Then without the absolute value is certainly going to converge. Like if all those terms are positive and it converges, well then that series is going to converge in general. So what this means is we always want to test this first. We always want to test for absolute convergence first, because if it converges absolutely, we're done. All right? If it doesn't, well then we have to test more stuff, which we'll get to. But we always want to test for absolute convergence first. All right. So this first series, it's an alternating series. So I want to test for absolute convergence. That's the first thing. Number one, I want to test for absolute convergence. And the way we're going to do that, we're just going to do that series, but put absolute value around it. Now, all that does, the absolute value, just undoes the -1, the alternating part. So that's going to be the same as the series of 1 over n to the 1/2. Now, we know that this is a divergent p-series because that p-value that right here is 1/2. It's less than 1. So we know it diverges. What that means is we've lost the absolute convergence. We know this does not converge absolutely, but does it still converge without the absolute value? Now we need to decide, does this thing converge? If this does, kind of like this did up here, if it does, then we say this converges conditionally. So what we need to do now is test if this converges, so we need to apply the alternating series test. So number 2, we need to test for conditional convergence by the alternating series test. That's what we're about to apply. So to apply the alternating series test, remember all we care about is the other stuff, not the -1 to the n. So we need to make sure a few things. We need to make sure that 1 over square root of n is positive, and it is, for n greater than or equal to 1. And then we need 2 things to be true. We need the limit of that, as n goes to infinity, we need that to be 0 to even have a chance. It does. And then we need the next term to be less than or equal to the previous term for some n value. So we need the next term to be less than or equal to the previous term for some n value. And we've talked about this ad nauseum. If the top numbers are the same, if we make the bottom bigger, then the whole fraction is smaller. And this is true for n greater than or equal to 1. Check. So it did not converge absolutely, but the actual series converges, so we say this series converges conditionally. It's conditionally convergent. I don't have an example on the notes here where one is absolutely convergent, but I can make one up really quickly by the same idea. If I did this, if I make that bottom exponent bigger than 1, so 2 or made it 3 right here, if I would take the absolute value of that, then we would just have 1 over n cubed, which does converge. So we would say this converges absolutely. So just to throw one in there. Last one. So we are going to be getting into factorial a good amount with the ratio test especially. The ratio test is going to be our friend with factorial. But I want to talk just a little bit. If I expand the first few terms, imagine I plug 0 in for all these n's right here. Well, I would get 0 factorial over 2 to the 0. And just one thing that's important to point out is, and maybe next class, if you remind me, I'll get into it a little more, but 0 factorial is actually 1. 0 factorial is 1, and 2 to the 0 is 1. So this is just 1. And then we would get minus, let's see, if I plug 1 in for the ends, I would get 1 factorial over 2 to the first. And then I would get, if I plug 2 in, I would get 2 factorial over 2 squared. There's a reason why I'm doing this here. And then I would get minus 3 factorial over 2 cubed plus dot, dot, dot. Okay. I'll explain this, why I did this here in a second. So the first thing I want to test for is absolute convergence. If I put absolute value around this, all that does is make the negative 1 to the n go away. So we would have n factorial over 2 to the n. So the reason I expanded this out, one thing we should know at this point is exponential functions always dominate polynomial functions. Let me say that again. Exponential functions always dominate polynomial functions. Meaning, if I had something like this is going to converge because this bottom number is going to dominate this top eventually. By that same token, factorials are the big daddy. Factorials dominate exponential functions eventually. And that's why I expanded this out a little bit, because you can kind of see what's happening here. This one says 1 over 2. Then this says 2 over 4. Then here I would get, this is 6 over 8. And then let's say I did one more. 4 factorial over 2 to the 4th. 4 factorial is 24. And this is 16. So just right here at 4, the factorial has overtaken the exponential. Factorials dominate exponentials. The reason that's a good thing is this right here is going to diverge because it's going to fail the nth term test. This is not going to approach 0. That top number is going to get big compared to the bottom number. So this diverges. Factorials dominate exponentials. So we lost the absolute convergence. We lost it. It's gone. But now we got to test for conditional convergence. So we're going to apply the alternating series test. So the other stuff is n factorial over 2 to the n. That's the non-alternating stuff. That is greater than 0. But if I take the limit of this as n goes to infinity, the top, again, this is just something we got to know, the top is going to get so much bigger compared to the bottom. Factorials dominate exponentials, which means this is going to go to infinity, which means diverges. That means the original series diverges. So with alternating series, you have 3 things that could happen. It could be absolutely convergent, it could be conditionally convergent, or it could be divergent from the get-go. All right. Goodbye.